Okay, so today we're going to talk about related rates, but first I want to just bring us back to an idea that we did on the very first day. You don't need to write this part down. But the very first equation we looked at in this course was the dragster, y equals 19x squared. And through graphing and all that sort of stuff, we actually did find the derivative, even though we weren't explicit that day. We we did actually find the derivative. If we were to find the derivative here, it would look something like this: y prime equals 38x. Or another notation instead of y prime is dy by dx equals 38x. Now, the derivative we know was the velocity, right? So the change in the distance ended up being velocity. Well, that is can be written another way. We used y and x because we were graphing it, and we really didn't have any. We wanted x and y to graph, but really the equation could have been this: 19 t squared, where d is distance and t is time, because technically it tells us how far, what distance has been traveled over a certain amount of time. Now, if we differentiate this, you could do this: d prime equals 38t. Or we could differentiate, instead of with respect to x, we would differentiate with respect to t, because that's the variable. So it actually feels kind of weird. It's dd by dt equals 38t. And that is just a little bit, it explains it a little bit more practical in real life. We are saying that this notation describes the change in distance as time changes. Okay, here it was the change in y as x changes, but really in this example it's the change in distance as time changes, which is what velocity is, the change in distance over time. So this idea is called a related rate. Okay, and we actually have a definition of that, and this is where you can start to write your notes. So a related rate is a change in time, happens, when a change in time causes a change in something else. In the dragster that we were just looking at, the change in time resulted in a change in distance. So we called that dd by dt. If we were looking just pure mathematically, when we do dy by dx, it's the change in x influences the change in y. But we're going to use this notation, this concept, in more realistic questions. And the two we're going to do today are related rates. So this d whatever by dt means the function is differentiated with respect to time instead of x. Okay? And that'll be important for today. So it could be a change in distance, which would be dd over dt, or if we use the displacement, the s from yesterday would be ds by dt. Or it could be dv by dt, which is a change in velocity with respect to time, and that would be acceleration. But it could be all sorts of other things, and you'll see that in the other examples we're going to do today. Okay, so here's the first example. You'll notice my star for the classic calculus questions. Both of these, example 1 and example 2, are classic calculus questions. So example 1 is when a pebble is dropped in a pool of still water, the area of the circular wave increases at a rate of 50 centimeters squared per second. So it's the area of the wave, the circular wave. So that we can imagine this. Actually, I'll show you a clip of one. But we know the area, we get this big circle, and that circle gets bigger. So we know how fast the area is changing. This question asks, how fast is the radius of that circle changing at a certain spot? So as you're copying that down, I'm just going to show you a quick video to demonstrate what I'm talking about. So it might be a little hard to see on the smartboard, but hopefully you can see that circle expanding. And we know the area of the circle expands. So we'll watch it again. Again, it's hard to see, but there's the circle, and you see that circle is getting bigger. So the area of the circle is increasing, and we know how big the area is increasing, and at the rate in which it is increasing. Our question is, I'm curious to how fast the radius is increasing. Okay. Now, there's a couple of things. Just like with the dragster, we, excuse me, I just need to stop this. Just like with the dragster, the speed in which the dragster is going depends on when we're talking. So the dragster at the beginning is changing. The rate of change at the beginning is different than the rate of change at the end. So you'll notice that this question isn't just asking how fast the radius is changing, but at a specific time, a snapshot. In this case, it's when the radius is exactly 50. Tell me how fast it's changing then. Not at the beginning, not at the end, just tell me how fast it's changing then. Okay? So I've drawn a circle, and this is just the first wave. We saw that there's lots of waves when we drop the pebble in there, but just the first wave that comes out when the pebble is dropped in the water. So we have this, and this wave is getting bigger, right? It's getting bigger this way, this way, this way, and this way. So it's spreading out, and we know the area is increasing at a certain rate. We're curious about how fast that radius is increasing at a specific time. In this case, it's when the radius is 5 centimeters. So I'm going to write down what we know. This is a great strategy when doing all sorts of word problems, is write down all of the information off to the side. So we've got a bunch of variables here. The first variable I see is radius. And at the specific snapshot, we're talking about a radius of 5 centimeters. We want to know how fast that is changing. So that's the derivative, and it's with respect to time. So that's the related rate. So we actually want to figure out dr by dt. dr by dt. So that's how fast the radius is changing with respect to time. That's the question. How fast the radius is changing with respect to time. What other information do we know? Well, we might know the area. We have that information. And we would know how fast the area is changing. So the formula for that is dA by dt. So this is how fast the area is changing with respect to time. So if I go back in the question, I see that dA by dt is this, because this is the area of the circular wave increases at a rate of 50 centimeters squared per second. The only thing that's not explicitly or given in the question is the area. And I could, if I wanted, to go off and find out the area at this specific time. I don't know if I'll need it yet, so I'm not going to solve it unless I need it. So this could be something I could do. I could just plug in pi r squared when r is 5 and figure out the area. But I'm going to wait and see if I need it. I do know that I need the rate at which it's changing, because that's given in the question. Okay, so to do this now, what I have to do is somehow find a formula that has all of these variables in it. Not the derivative parts, just the a and the r. And when I think about it in this case, I know a formula that does that. It's a equals pi r squared. So you'll need to pick a formula or an equation or whatever that has our variables. So this was easy because the question had area in it and it asked about the radius. So I'm going to use the area formula for a circle. In another question, I might be talking about a square increasing. So I would use the area of a square. Or maybe I'm talking about the volume of a cylinder increasing. So I would use the volume formula. Either way, I have to find some formula that has all of these variables in it. And this is a nice one, a equals pi r squared. Now, I need the dr by dt and the dA by dt. This formula doesn't have it. But if I differentiate this, the dRs and the dTs will pop up. So next is we're going to differentiate implicit differentiation. We're going to implicitly differentiate with respect to time. Because we want how each of the variables is changing with respect to time. I don't care that there's no t in the equation. I'm going to differentiate with respect to time. So when I take my a equals pi r squared, I'm going to look at the a and take the derivative of a. So the derivative of a is just 1, except I'm differentiating with respect to time, so it's dA by dt. Remember yesterday, we differentiated with respect to x, and any y's ended up being dy by dt. In this case, I'm differentiating a with respect to t, so I take the derivative, which is just plain old 1, and then I got to write down dA by dt. Over here, notice that this is actually just a number, right? Pi is not a variable, it's a number. It's 3.14159 and so forth. So this is just a simple differentiation. 2 gets multiplied by your number, so it's 2 pi r, and then it's to the power of 1, 1 less. Except I'm differentiating with respect to t, so it's dr by dt. Just as a side note, the derivative of this, it's the same as if it was 4r squared, right? It would be 4 times 2 is 8r. But it's not, it's pi r squared, so it's pi times 2, which is 2 pi r. Okay, same math. Now, I have now a calculus statement, and the calculus statement introduces these related rates, which is good because this is the thing I want. I want dr by dt. Now I'm going to go through the rest of the equation and make sure I have all the other known variables. Do I have dA by dt? Yep, it's right there. It's 50. Do I have pi? Sure. Do I have r? Yes, it's right here. Sometimes I might need a, so I would go off and do it, but it turns out I don't need a. I just need dA by dt. So now the math is relatively easy at this point. I start substituting. I don't need the 1 anymore. I'm going to replace this with 50. And 2 pi is just 3.14. R is 5, so I'm going to replace the 5. And then this is my unknown, so I'm going to leave it as dr by dt. Math is pretty easy at this point. 10 pi dr by dt. Divide both sides by 10 pi, and I get 50 divided by 10 pi. And in this case, I mean, that's a great answer. We could reduce the fraction, 5 over pi, but really, it's a real-life scenario, so we'd like to actually figure it out. So, I mean, you could say it's 5 over pi. This would be the exact answer, but I'm curious of actually what the number is. So I can go to my calculator and just 5 divided by the pi button, and I would get 1.59 centimeters per second is dr by dt. So therefore, the radius is increasing at a rate of 1.59 centimeters per second. I know the units because the question was given with centimeters here and here, and the rate was in per seconds. So I know it's 1.59 centimeters per second. So just recapping, I take the question, maybe I draw a picture, it might be helpful. Write down what I know. There might be stuff that I don't know, but before I solve for it, I'm just going to see if I need it. So I wrote down the radius and all of the corresponding related rates. So any variable you have, write down the related rate. If you know it, then great. If not, that might be what you're asked to find. Then you choose some function that can be differentiated or some equation. In this case, and make sure that equation has your variables in it. So in this case, I chose a equals pi r squared. Took the derivative with respect to t, which introduced this whole dA by dt and dr by dt. And then I could substitute and solve.